we believe that in the process there will be laminar flow. Then at some point, after maybe the fluid has traveled quite a bit, traversed quite a long length of that pipe, there could be turbulence developing. So there could be a turbulent flow. So first of all, let us start by just drawing what we think the profile will be when this fluid is flowing in the tube. But let's just note that talking of fluid flowing in a cylindrical tube of diameter d and radius r. Now, let us draw a schematic of how the flow, as the fluid flows, the velocity profile develops. Just a schematic. Development velocity profile. So we have our pipe. See if we can draw it better. So we have our pipe. So this is our pipe. So at the inlet here, inlet, at the inlet there we have an irrotational flow. At the inlet we have an irrotational flow. Let's just note that. Irrotational flow. And that's a very important term. So inlet region, so irrotational flow. So we have the irrotational flow at the inlet. So why do we emphasize the word irrotational? Irrotational, just from ordinary English language, means something which does not rotate. So precisely what we are saying is that at the entry of the fluid into this tube, those elements in the fluid, the elements in the fluid do not rotate. They do not rotate about their center of mass. The elements, the fluid, do not rotate about their center of mass. That's what we mean by irrotational flow. Now, the only time when, for example, you'll have those rotational flows is, for example, if the shear forces at the wall, the torque resulting from the shear forces at the wall, that can affect rotation. But other than that, minus shear forces at the wall, then we don't expect that there will be any form of rotation of the elements in that fluid, which is entering that system or flowing in that system. And don't forget the shear stress. We had already said tau for shear stress in general is mu du dy, and of course there's that R is also the same as rho v du dy. Don't forget that. Always remember that. where mu is dynamic viscosity, and here V is kinematic viscosity. Now, we have just said if there are shear forces, torque resulting from the shear forces at the wall between the wall and the fluid, then of course there is a possibility of rotation. Otherwise, we assume that the fluid which is getting in at the inlet is not rotating. The elements in that fluid are not rotating at all about their center of mass. Now, as we progress, what does that mean? As the fluid flows within the tube, we are developing the velocity profile. We now know what the velocity profile is from our earlier lectures. And I continue to keep reminding you that it's important that you go through all our lectures systematically so that we are together. Now, the velocity profile will develop. Let's just indicate that. So here we have the velocity profile. The velocity profile is developing. So let's call this the average velocity. That's a developing velocity profile. Velocity profile. It's a developing velocity profile. And so we are saying that as the fluid continues flowing in the tube, the velocity profile develops, and we'll finally have even laminar flow. Have a laminar flow, average velocity. Now we have laminar velocity profile. And let us say that this occurs at some distance from the entrance, which we call LC. LC. Distance from the profile. Remember, the axis of the tube is here. That's the axis of the tube. That's our axis of the tube. And so let us say that some distance LC from the entrance, we now start developing our laminar flow. Now, this laminar flow normally will be in the region where the Reynolds number, we are going to talk about it again, the Reynolds number is either less or equal to 2,300, the region of the laminar flow. And then, of course, as we continue, distances away, further away, you can develop a turbulent flow. Develop a turbulent flow. Our velocity, this is turbulent velocity profile. And of course, here is where we'll have maximum velocity. We'll have maximum velocity. And you can see the gradient of the change velocity here is quite high, and here quite small, du by dy. And of course, in these regions, Reynolds number is greater than 2300. I repeat, we are having our fluid gets into the tube. We have the inlet region, and we are saying that we are assuming that the fluid is rotational. In other words, the elements in that fluid do not rotate at their center. That's at their mass, center of mass. They do not rotate at that particular point unless there are probably some torque applied as a result of shear stress at the walls there, at the wall there. So, as the fluid continues flowing, we develop the velocity profile. And we are saying that after probably some distance, LC from the entrance, then we'll have started developing fully the profile. So fully developed, let us say this region now have a fully developed velocity profile. And so we have our laminar velocity flow, and of course, after a period, we can expect turbulence to set in, and we have already talked of what could be some of the causes of turbulence. That's velocity gradients within the fluid flowing, creating eddies, and of course, then the turbulence picks up. And of course, the Reynolds number becomes large. Now, if the diameter of the tube, if we say the diameter of the tube is D, diameter of the tube is D, and its radius is R, which we determined is at the center of its axis there, center of axis of that particular tube. Then, if, as you have already assumed in our earlier lectures, when we were talking about the various boundary layers, we said that the velocity profile here, the laminar velocity profile at the interfacial boundary, we say that that behavior, that profile can be described by a parabolic equation. So we are saying that in the laminar velocity profile region, the interfacial boundary can be described by a parabolic equation. And so this parabolic equation can be expressed in terms of this distance, which we have talked about as LC, and the diameter of the tube, so that that expression for that fluid flow will be for the interface, for that interfacial boundary, the equation will be LC over the diameter, and that will be given by Y over R, Y over R squared, where R is that radius on the axis tube, radius, axis of the tube. That's from that wall to the axis of the flow. And then, of course, that's the diameter. Now, This is the parabolic expression which we have said in terms of that, in terms of these particular quantities. So that this parabolic equation should describe the fluid flow in this particular tube. And now, we can talk of the mean velocity. For example, we indicated that the velocity is maximum at the peak there. We can talk of the mean, we can talk of the mean velocity, the weighted mean velocity. That is a lot easier than to find that uniform velocity in that particular tube. So, using the weighted mean velocity, we have this particular case. No, we have sorry for that. It's our ratio, mean velocity, and that our LC over D is 0.028 of the Reynolds number. That expression of the parabolic equation is given in terms of the velocities. And so here we have the uniform velocity. The uniform velocity is very difficult to compute. So we want to we want to deal with average velocities or the weighted mean velocity. That would be a little bit easier to compute than just the uniform velocity to do with the system. And that LC over D, that length there, we said LC over D is 0.028 of the rate times the Reynolds number. And of course, this relationship is U over UR to Y over R squared. And remember, we have already seen this type of equation in the past when we were developing our initial velocity profile in the earlier flows, where we have seen that our velocity U over UR was actually 3 over 2 Y over sigma minus half Y over sigma cubed, where of course the sigma was the boundary layer thickness. Remember that? That's where we first met this particular expression, this type, where we had combined the Navier-Stokes equation and the Bernoulli principle. And so in the tube there, this is the parabolic equation which accounts for the ratio of these two velocities. Now, and of course the L over C, LC over D is, in terms of Reynolds number, is 0.028 times the Reynolds number. Now, let's look at that Reynolds number. Now, what is this Reynolds number? Reynolds number, remember, we have already mentioned it. We said the Reynolds number is kind of the one which helps you figure out the flow pattern of a fluid. In other words, it gives you the ratio between the inertial forces and the viscosity or viscous forces. That is, Reynolds number is density times the velocity times the displacement. In this particular case, it is the diameter. And that is over the dynamic viscosity. And it, here rho is density, mu m is mean velocity, d of course is the diameter of the tube, and mu is the dynamic viscosity. So it gives you a ratio between the inertial forces and the viscous forces. So in a nutshell, we don't need this anymore. Let's just leave it there. We might need it. You don't have to draw it again if in case you need it. So in a nutshell, just note that Reynolds number gives the fluid flow pattern and it's basically a ratio between inertial forces and viscous forces. So Reynolds number is a very important quantity. And for flowing tubes, the Reynolds number should not exceed 2,300. Should not exceed 2,300. Now, how do we compute the mean velocity? How do we compute the mean velocity? How do you compute the mean velocity? Computing mean velocity. So very simple. Mean is always implying that you're dealing with averages. So we integrate this particular quantity, then you end up with that expression there. And we have the mean velocity there. And this particular expression which you have here is the mass flow rate, and that you can tell simply from dimension analysis. We show you that this quantity here is mass flow rate, that is the density. What is density? Because remember, rho is density, just in case we're lost to density. M, not mu, M. M is mean velocity. And A is area, the flow. So what do we have? So if you have in that particular case, in terms of units, we have mass over volume, and we have velocity, which is some unit of length per unit time. Let's just call it length over time. And area is length squared. So that's length cubed, should cancel the volume, so you have mass over time. And anytime you have mass, anytime you see time involved, then the word rate comes in. Anytime you see the word rate, always know time element is there. And so this becomes the mass flow rate. That becomes the mass flow rate. And so that's very important. So we have seen several important things which we need to mention. One, when we have our fluid flowing through a tube, we're assuming the tube has some diameter d and its radius relative to the axis of flow is r, let us say. Now, when the fluid gets in, we're assuming that the elements in the fluid do not rotate at all, the center of mass. So it's irrotational fluid. But like we have said, if there is significant torque applied from the shear forces at the walls, then of course there will be rotation. Otherwise, as the fluid progressively moves on, the profile is developing. The profile will be developing. And after some distance about which you are calling from the entrance, what we can call this, you can call this entrance length. We just call it entrance length. We start having the development of the laminar velocity profile. And so that LC divided by D will give us that quantity which we have seen was 0.028 Reynolds number. And we have said that the velocity profile can be described at the interface, the interfacial boundary of that boundary can be described by a parabolic equation, which we have already seen. We have already said that parabolic equation, which is the ratio of those velocities, will be given by 2y over r minus y over r squared. This describes that interface, the facial boundary, the profile, the interfacial boundary. And we had already seen that for others, for velocity, when you are dealing with the velocity boundary layer earlier on. So kindly please try to go through those lectures. And we are saying that this occurs at Reynolds number less than 2,300. And we have said Reynolds number is very important in determining, in giving you a feel or giving you a picture of the flow pattern. And of course, it's basically the ratio of the inertial and viscous forces. Now, and we are saying that in the laminar flow region, RE, the Reynolds number should be less than 2,300. Of course, as the flow continues, and like you have said, there could be velocity gradients developing within the system, and if this happens, then the eddies are created, and all that happens is the turbulence is introduced in the system naturally, and so that normally occurs at much higher Reynolds numbers, So normally the Reynolds number in the flow, for the fluid flowing in a tube, should be about 2,300. It should not go beyond that. It should not go beyond that particular case. And one of the things which we have now seen is that there is progressive development of the velocity profile. So you don't get the velocity profile, laminar flow velocity profile. Doesn't develop at the entrance straight away that you'll have laminar flow. It develops gradually as the fluid flows through the system. Let's stop at that particular point. We are continuing with our thermodynamic lectures.